Thank you. Got it. All right, got it. Well, thank you, and thank the SGA students for inviting me to speak to you guys today. One thing before we start, the next SGA conference is actually going to be here at the Colorado School of Mines in August of 2025, with a lot of good field trips, a lot of good workshops, and hopefully some of you will attend and participate here in Colorado where we have the next SGA meeting. So what I want to talk to you about today is, as you heard, I do a lot of work on orogenic gold deposits. So I want to talk about orogenic gold deposits, and I'll talk a little about other deposit types. But one of the main conclusions, especially as it relates to orogenic gold deposits, if your gold deposit formed below 3 kilometers, which is the case for almost all orogenic gold or gold and metamorphic rocks, it cannot be intrusion related. And hopefully that is one point I can get across in this talk today. There's a lot of confusion in the literature. There's a lot of erroneous information in the literature. And especially as students, you have to be careful. Anything gets published today, whether it's right or wrong, and you need to judge. And some of the things I will talk about today sort of point out what kind of things may be wrong in the literature. So let me move ahead here. Let me see how I can move ahead. Whoop, oh, there we go, the next slide. This is an old slide from maybe 25 years ago, but it really stresses there's really only two ways that we can form gold deposits on this planet. You know, people like to have all these fancy models, but there's only two ways that you can get fluid to form a gold deposit. First, and many of you in Colombia are very familiar with these type of deposits, you can have intrusion-related or magmatic hydrothermal deposits. In those cases, you take a magma, you place it at very shallow levels, often for gold at 3 kilometers or shallower, and you can have fluid escaping from the top of the magma, sometimes mixing with surface fluids, forming porphyry deposits at the top of the crystallizing magma, or at shallower levels, your epithermal gold deposits. So in this case, the fluids are magmatic hydrothermal and or sometimes meteoric. The heat source is a local heat source, an intrusion, and the deposits form in the upper 3 kilometers of the crust. The deepest economic porphyry deposits with gold are at 3 kilometers. Gold-bearing porphyries tend to form at 2-3 kilometers. A second way to form gold deposits on the planet is as you metamorphose rocks. You bury rocks, you heat rocks. Rocks like shales and basalts turn into greenstones and argillites. And as you metamorphose a rock, 3 to 4% of that rock volume changes to fluid. That fluid may move into large fault zones. During seismic events, the fluid may move up 500 meters or 1 kilometer and form orogenic gold deposits that can form as shallow as 3 kilometers or as deep as 15, 20 kilometers. So in this case, there's no local heat source. It's the regional geothermal gradient creating the fluid. The fluid is metamorphic, and the deposits form anywhere from 3 to 15 to 20 kilometers, with differences I'll talk about depending on the depth that they form at. And that's the only two ways you can form a gold deposit. Either the fluids are unmixing from a magma, or they're produced during metamorphism. There is nothing else. And half of what we target on our planet are the orogenic gold deposits in metamorphic rocks or metamorphic terrains, which includes in Colombia your important Segovia, or Frontino gold belt. And that's about half of the world's gold endowment, ignoring the great paleoplaces of South Africa, which are a unique deposit type. The other half of the deposits that have gold on our planet, the other half of the gold endowment, are the epithermal and porphyry deposits, or intrusion-related deposits. So basically, we have two types of fluids, metamorphic and magmatic, and we have two types of gold deposits. The problem is, many geologists like to more or less have a point source. They want to say, I know where that water came from that formed that gold deposit. So if you have a gold deposit, say up here, and you have a granite here, or maybe a stock here, or maybe a dike here, geologists like to point to these, or point somewhere buried and say, I know there's a buried granite in the geophysics. It must be the source of the gold forming fluid. And that is incorrect. If these gold deposits formed at 5 or 10 kilometers, these magmatic rocks cannot be the source of the gold forming fluid. But it's hard for many geologists to understand, or economic geologists, that a metamorphic fluid can form orogenic gold. And that's what I'll talk about today, because we're talking about a regional fluid that's part of orogeny, and you can't point to a little local source like a granite releasing fluid. We're talking about fluid created over a broad region. Now, if we look at in space and time for intrusion-related versus orogenic gold deposits, we see very different patterns. If we look at the spatial distribution of intrusion-related deposits, we see they're on two places on our planet. They're associated with the circum-Pacific arcs. They can be oceanic arcs, such as here in the Southwest Pacific. They can be continental arcs, such as in the Andes, which many of you are more familiar with than me. And those are the young arcs along the circum-Pacific. Another young arc belt goes from Western Europe and Turkey all the way to Tibet and Yunnan and China. And that's the young Tethyan belt between Africa and Europe. And that's where most of our gold endowment sits, that is intrusion related. And it's a much different distribution than our orogenic gold deposits, which are all over the planet and of all sorts of ages. These intrusion-related deposits are almost all Cenozoic in age. The orogenic deposits are all over the planet in all sorts of ages. The deposits that are tertiary and Mesozoic run from Nome, Alaska, actually down to the Segovia Belt in Colombia, and they run from eastern Russia down to the South Island, New Zealand. Paleozoic orogenic gold deposits are widespread throughout Central Asia. Paleoproterozoic orogenic gold deposits are in northern Australia. They're here in places like Homestake in the central part of North America, and they include the great Paleoproterozoic gold province of West Africa, some of which has rifted away and includes the Paleoproterozoic deposits that now sit in northern South America, from northeast Brazil all the way across to Venezuela. And then we have late Archean orogenic gold deposits, which are in central Canada, which are in Brazil, which are in much of Central Africa, India, and Western Australia. So unlike the intrusion-related deposits, these are all sorts of ages and all over our planet. And when we look at the age distribution, then this is what we see. The endowment, as I said, in intrusion-related versus orogenic gold is about the same. However, the intrusion-related deposits are all relatively young, Cenozoic, with some a little older, but not a lot of the endowment. Most of the endowment is very young, as opposed to orogenic gold deposits, which are spread back through the geologic record. So when we talk about Paleozoic gold, Paleoproterozoic gold, Archean gold, we're almost always talking about orogenic gold. And also, you'll note, no matter what the gold deposit type is, between about 1.7 and 0.7 billion years, there are no gold deposits. We do not explore for deposits in those age rocks. There are a few exceptions I'll talk about later, but for the most part, you will not explore in Mesoproterozoic and early to middle Neoproterozoic rocks. Now, just briefly on the intrusion-related deposits, because I'm not going to focus on those, and many of you know these from work in Colombia. There are two types of epithermal type deposits that are associated with magmatic centers. These deposits form maybe at 1 to 2 kilometers depth. They look very different. There's low sulfidation epithermal deposits and high sulfidation epithermal deposits. The high sulfidation deposits, because the fluids are all acidic magmatic, leach the rocks of everything. And so you just have this silica sulfide alteration. And this was first pointed out by Dick Silito and Jeff Henquist. And this has been understood now for probably 50 years. There had been controversy in that the high sulfidation deposits, people recognized were magmatic. That's why we saw the high sulfidation, the leaching of the rocks. But these low sulfidation veins, people argued, well, they could be just surface water being heated by the intrusions and depositing these low sulfidation veins at 1-2 kilometers depth. But a lot of lead isotope data shows that the sulfur, that shows that the lead in these low sulfidation deposits has the same source as the high sulfidation deposits. It's magmatic in origin. So the low sulfidation deposits also get their gold escaping from the top of the magmas at 3 kilometers or shallower. They, however, mix with meteoric water, and the meteoric water neutralizes the fluids. So we have these low sulfidation veins rather than the high sulfidation textures. But the gold in both cases is released with fluids from magma, generally at 3 kilometers or shallower depth. One of the reasons we don't have porphyry or epithermal deposits forming at deeper levels, the levels that we form orogenic gold deposits, is below about 5 or 6 kilometers, water is soluble in magma. So if you're below about 5 kilometers depth, you're not going to form a mineral deposit from a magma releasing fluid, because that fluid is dissolved in melt. And too often, economic geologists ignore that and still like to say, well, I have a granite at 10 kilometers, an orogenic gold deposit formed at 9 kilometers. There must be an association. There is no association because the water cannot escape the melt till you get to shallower levels. And in fact, that's why our deepest porphyries are moly porphyries at 5-6 kilometers, or our copper-bearing porphyries maybe at 4 or 5 kilometers, or the deepest gold-bearing copper porphyries are often at 3 kilometers or 2.5 kilometers, where fluids escape from the top of a magma. The pressure builds, you build up pressure, you fracture the top, the cupola to the granite and the adjacent host rocks, and you have your stockworks and your gold deposits. But you're not going to form these at the depths that orogenic gold deposits form because the fluids are still in the melt. And there are examples where you can have a supersaturated magma where you may release some water at depth below 5-6 kilometers. But that water, because you crystallize inward, moves up the mush and still escapes at the shallow levels rather than forming porphyry and epithermal deposits on the sides of a magma chamber. And if we look at some classic recent work by Massimo on porphyries, he pointed out what I've been saying is that you don't degas a magma till about 4 or 5 kilometers, And those here in orange or red, whatever color this is, are your deepest copper porphyry deposits. We don't start getting economic gold till we're 2-3 kilometers. The gold doesn't escape with the fluids till those levels. So the deepest economic gold deposits from a magma are at 2-3 kilometers, and orogenic gold deposits form deeper. And so we'll get to that in a little bit when we talk about sources for fluids in orogenic gold. So unlike intrusion-related deposits where we see the granites right nearby, and we understand well how porphyry and epithermal deposits relate to the granites, orogenic gold deposits are more controversial because they form at deeper levels. And so it's much harder to understand what is going on, especially because there's no spatial association with a causative granite, even though many people like to show granites related to orogenic gold. So that's one reason it's controversial. Also, Carlin-type deposits, I'll talk briefly at the end about, which are very important in Nevada, USA. Carlin deposits are also controversial because they're less common. Our models for porphyry, epithermal, orogenic gold are based on thousands of studies of gold deposits around the world. The Carlin deposit model is based on many studies in Nevada, USA. So it's a local model. Can Carlin deposits be Archean? Who knows? Can you find Carlin deposits in Colombia? Who knows? Because this is a local model. And that's why Carlins remain controversial. So deep deposits, local models definitely have led to controversy in our understanding of some gold deposit types. So let's talk about orogenic gold deposits. Orogenic gold deposits are simply a term for gold in metamorphic rocks. That's what we're talking about. Historically, these were high-grade, low-tonnage deposits, but now we can mine these very low-grade but high tonnage. This is Morro de Oro or Paracatu in Brazil. It's Brazil's largest gold deposit. It's an orogenic gold deposit. It's being mined at 450 ppb, a 0.45 grams per ton. When I started studying gold deposits, this was a geochemical anomaly. Now it's a 20 million ounce deposit. The host rocks for orogenic gold, though, have changed over time, and let's talk about that. The deposits are still the same, but they form in different host terrains. Most Precambrian orogenic gold deposits are in greenstone belts or metavolcanic rocks. That's because most of the continents, or 75% of the continents, are made up of Archean and Proterozoic rocks that are core to the continents. And on the early Earth, when it was hotter, we often had rifting, opening of oceanic basins in the continents, and then reclosing those basins and metamorphosing the volcanic rocks associated with the rifting. And so most of the older orogenic gold deposits are in metamorphosed volcanic terrains or greenstone belts, especially where we have sheared mafic and intermediate volcanic rocks and granite gneiss basement terrains. Green schist facies rocks, this is Western Australia. Here's an example from India, high-grade basement, and shearing of these volcanic belts within the high-grade basement. And that's where many of our Precambrian orogenic gold deposits are located. In contrast, when we look at Phanerozoic orogenic gold deposits, they're not hosted in metavolcanic dominated terrains. They're hosted in metasedimentary rock terrains, in argillites and gray rackies, oceanic rocks. They can be adjacent to large subduction batholiths, both on the margin of the batholith, such as in Segovia or Pataz here in nearby Peru, or they can be in the sediments adjacent to the batholiths, but these are mainly sedimentary rock types. Now, the reason for the difference is over time, plate tectonics has changed. Again, in the Precambrian, Where the Earth was hotter, we had plume tectonics, we had rifting, and we had closed the rift basins and metamorphosed ultramafic and mafic rocks, which host most of the older orogenic deposits. Though as the Earth cooled, beginning about 1.6, 1.7 billion years, rather than collision between blocks, we were able to start subducting on a cooler Earth oceanic rocks. And then new material added to the margin of the continents are oceanic rocks that are being metamorphosed. So 75% of the continents are volcanic rocks of Precambrian age. 25% of the continents are these Cordilleran-style belts, like you have in the Eastern Cordillera of Colombia, that have been accreted to the continental margin as sediments once you could start having subduction. So the rocks that have been metamorphosed and deformed to host orogenic gold were dominantly volcanic on the older Earth, sedimentary on the younger Earth. That doesn't make the deposits any different, but the host rocks have changed over time. Now, to explore for these orogenic gold deposits, there's three things that are very important: structure, metamorphism, and traps. And these are the kind of things you need to think about when you explore for orogenic gold. Unlike intrusion-related deposits, where you're looking for a specific age of a granite or a specific type of a granite, in orogenic world, you're looking to try to understand the structural geology. Structure is critical for orogenic gold deposits. Large orogenic gold deposits need large river channels or large faults in the crust. Western Australia, the gold deposits sit here along the Boulder-Lefroy Fault, including the Golden Mile here at Kalgoorlie, the world's largest orogenic gold deposit. We go to the Paleoproterozoic of West Africa. On the margin of these basins, sedimentary basins with the volcanic rocks, we have shearing and orogenic gold deposits along these regional shear faults that go for hundreds of kilometers. And in Juneau, where I worked for a long time, very young gold deposits, Eocene age. The largest orogenic gold deposits sit along this major fault zone, some here behind the town of Juneau, built on mine tailings up this valley, some on another terrain on the other side of the structure. You can see the old mine pits here that had 3 million ounces of gold on the other side of this structure. This is a major structure with fluids that came up the structure and formed orogenic gold deposits on the same day on opposite sides of the structure. So spatial association with structures is important. Now, you're always going to create a lot of fluid during metamorphism, but if you don't have major structures, fluids can go everywhere, and you'll have lots of small little veins like Klondike in Yukon, Canada. It produced and is still producing 20 million ounces of placer gold, but it has high-grade little veins everywhere rather than fluids focused along a major structure. And so it has great alluvial potential, but not load potential. You need these big structures to have load potential. And these structures go for 500 kilometers or even longer. So where are you going to explore? If you're going out there, and this may hold many of the faults in the Eastern Cordillera of Colombia, you want to look at structural trends. This is that Boulder-Lefroy Fault I talked about in Western Australia. It strikes 155 to 165 degrees. But you can see wherever there's a change in strike of 10, 15, 20 degrees, that's where the gold deposits sit, including the Golden Mile, that giant orogenic gold deposit in Western Australia. Because where you have these changes in strike, you get second and third order faults and fold systems shearing and splaying off these, and that's where the gold deposits will be located. Not in the first order faults, but a few kilometers off the first order faults in second order systems. I've been working a lot recently in northern Finland and Lapland. The Kitla mine here, 8-9 million ounces of gold, is the largest gold deposit now in Europe. And it sits where there's a 20-degree bend in this regional north-south fault system. You want to look at jogs. Before you go to the field, look at your maps. see where there's major bends in the fault systems. Those bends open spaces, and that's where fluids are going to go, and that's where you should focus a lot of your exploration. And certainly structural complexity is very, very important. We want to look for a lot of changes in the stress field over the 5 or 10 million years a major gold deposit can form. This is, again, that giant gold deposit in Western Australia, the Golden Mile. And during a 10 million year period, we had compression, formation of thrust faults and regional folds. Then we had sinistral strike slip, and we formed the Golden Mile, the eastern lode system and the western lode system, that giant open pit I showed you. Then we have a change to further thrusting, and then we had a change to dextral strike slip, and we formed these large Mount Charlotte type gold deposits up here. So you want to have a lot of changes in stresses. The more complex, the more space you open, the more important the gold deposit. We can see that in Peru also, just to the south of you, where we had thrust faulting, we had terrain accretion, we had changes to strike slip and sinistral strike slip, and formation of the orogenic gold deposits in the margin of the Pataz batholith. You want to see changes in stresses. You want to see structural complexity. You don't want simple geometry. More complex, the better. And then again, we want to look in second and third order structures for these deposits. They can be steep fault fill faults and extensional faults. Here you can see examples of this. This is from the Mother Lode system in California. But you build up fluid pressure along a fault, and you start forming these extensional veins as fluids start to exceed hydrostatic pressure and open spaces in the rock. Once these fluids, though, exceed lithostatic pressure, you form a fracture and you deposit silica and gold. And then that seals the fault. And then that drop in pressure, you start building pressure again and have more extensional veins, more fractures and fault fill veins, more extensional veins. This is what people like Francois Robert and Rick Simpson refer to as fluid cycling. And so you go back and forth, and a large orogenic gold deposit or province, say like Segovia, might form over 2, 5, 10 million years as you go back and forth with this fluid cycling. Now, many of these second order structures also intersect with regional fold systems. Fluids may move up the limbs of anticlines and deposit orogenic gold along the limbs of the anticlines, or you may fracture the top often of these anticline systems and form deposits along the sheared faults on top of the anticlines. What's most important in all these orogenic gold deposits, all these second and third order shears, all these localization of orogenic gold is often between units. For example, here you can see in West Africa, in the Ashanti Belt, over here on this side, we have metasediments. On this side, we have metabasalts. You can see how they're bleached near the contact. And the mineralization sits along the shearing between the contacts. You want to look for sheared contacts. In covered terrain, your geophysics will show this. Sometimes the contact will be between a granite and an argillite, and the mineralization will be in the granite. This is a whole province here in Burkina Faso in Western Australia. And look where the deposits are located. It's no coincidence. You can look at a geology map and predict. For example, here we have a contact between granite and conglomerate, and here we have a deposit. We can look here, and we have a sheared hinge zone to an anticline. We have a deposit. Here we have a second order splay off a major fault, and we have a gold deposit. Here we have a contact between graphite and basalt, and we have a gold deposit. Here you can see a major jog along the fault, and we have a deposit. So knowing these things, you can go out and look at your geologic map and sort of predict the best places to explore, the best places to do your geophysics, to do your geochemistry. You may be trying to study a broad region, but there are hints where to go explore in that region. I've recently been doing a lot of work again up in Lapland, and these are just some deposits up there that show you the same thing. We have a contact here between metabasalt and ultramafic rock, and here we have a mafic schist that's sheared between these two units, and that's where the major mineralization sits, especially where we have small granite plugs in here that are very brittle fracture, and much of the mineralization is in there. We can look at that Kittler deposit I talked about, which is the largest deposit in Europe. We have two tholeiitic basalt units, and we have a mylonitic zone of argillite, a narrow zone sheared between these, and that along this Kittler shear zone is where the mineralization is located. You want to look for contrasts between units. And again, also, we want to look at regional folds, anticlines, because that's where much of the mineralization is, especially where the folds are locked up tightly. Broad folds are not as productive. You want folds that are like 20, 30 degrees, which really enhances fluid movement, fracturing, and formation of orogenic gold. And a key to moving fluids is changes in far field stresses. This is work we did in Juneau 30 years ago now, and you can see it holds all the way back to the Middle Archean. People have shown this has happened in Barberton in southern Africa. Basically, change in plate motion. Before 56 million years, we had subduction along the margin of North America. We had rocks being subducted, metamorphosed, fluids held tight in pore spaces as you had compression. From plate reconstruction data, though, we saw there was a major change in plate motion in the Pacific Basin from 56 to 55 million years, where we changed to strike slip and a more oblique subduction. Once you do that, you start having regional uplift. Once you have uplift, rock pressure decreases relative to fluid pressure, and you can start having fluid fracturing the rock, moving into major faults horizontally down pressure gradients, and then moving up during seismic events to form your orogenic gold that then is uplifted over tens of millions of years to what is now at the surface. So changes in far field stresses allow earthquakes, and that leads to formation of orogenic gold. Now, if you look at these worldwide, here's examples from the Yulgan and the Superior province, but I can show this from anywhere. The bulk of the gold sits in medium-grade metamorphic rocks, green schist, some in upper prehnite pumpellite, some just into lower amphibolite. This is the Juneau area. Again, these were the two deposits on opposite sides. We have a Barrovian, a moderate to high temperature geothermal gradient. The gold sits in green schist facies rocks. So along these structures, you want to look for rocks that expose green schist facies, because that's where your orogenic gold sits. Now, it does confuse a lot of people, and early on when we produced a metamorphic model, people had major problems saying, well, the orogenic gold deposits post-date metamorphism of the host rocks. So how can you say it's a metamorphic fluid? But in a belt, in a metamorphic belt, metamorphism doesn't happen at the same time everywhere. Some rocks are subducting and being metamorphosed at depth, as other rocks that have passed that peak of metamorphism 5, 10, 20 million years earlier are uplifting. So fluids are being produced at depth. They move into these major faults and deposit gold in rocks that have already been metamorphosed. So orogenic gold deposits, even though, as I'll show you in a few minutes, form from metamorphic fluids, they always post-date metamorphism of their host rocks. Fluids move from a prograde to a retrograde region of an evolving orogenic belt. And also what is important is that most pressure, temperature, time paths for orogenic belts go like this. So you bury a rock to high pressure, and then you start uplifting it. And for 10, 20, or 50 million years, that uplift is either isothermal or a slight increase in temperature. So fluids can fracture the rock as pressure is decreasing, rock pressure relative to fluid pressure, but temperature is not important. Unlike magmatic deposits, where you're looking at a thermal gradient and cooling away from a granite, in the orogenic world, you're looking at temperatures that are not decreasing as the orogenic gold deposits are forming. You may uplift from 20 kilometers to 3 kilometers, and somewhere along that path over tens of millions of years, you're forming your orogenic gold deposits, but temperature is not decreasing. So temperature is not important. So we want to look along major structures, and we want to look in green schist facies rocks. And then again, we want to think about traps. If we have a competent rock, such as a granite batholith, in argillite, the granite fractures more easily, open space, and you form your orogenic gold deposit in what's called a physical trap. This is the Alaska Juneau mine. You can see the added here for scale. Here's argillite, and here's large intrusive bodies. And you can see how 95% of mineralization are in these quartz veins in this brittle intrusion. The intrusion is 150 million years older than the gold deposits, but it's a favorable physical host. It's not an intrusion-related deposit. It's an intrusion-hosted deposit, similar to what you would have perhaps in Segovia. And then if you're exploring undercover, if you're in this argillite terrain, you want to look for these intrusions, not because they're favorable source rocks for the gold, but they're favorable physical traps, they're favorable hosts. You can see the same thing in many, many places in the world. We can go to Pataz. Some people like to call this intrusion related. No, Pataz in Peru is intrusion hosted. This batholith is 340 million years. The veins formed as the batholith was uplifting 20, 25 million years after the batholith crystallized and was brittle and the fluids could move into it. So these are physical traps. In contrast, we also have chemical traps. This is the 40 million ounce Homestake deposit in the US. And these are all a series of Proterozoic formations. But fluids have moved up on folds in these Proterozoic rocks. And you can see how all the mineralization here in black is in this one thin formation called the Homestake formation. Why? It's a banded iron formation. The fluids hit this iron-rich rock, and sulfur is carrying the gold in a metamorphic fluid. The sulfur reacts with the iron, drops out pyrite and arsenopyrite, and the gold comes out of solution. So it's a good chemical trap. Now, if we look at orogenic gold deposits, sometimes they may look really different. And people like to say, oh, these are different deposits. No, they're just different host rocks. You can look at an argillite that hosts orogenic gold. It looks like this, these beautiful laminated quartz veins, with each of these representing deposits of silica, then breaking off a piece of wall rock. This may be some of the argillite, then more silica, then more argillite, reflecting maybe 100 earthquakes over 3 million years. However, you can go across a fault and look in a more brittle rock, and you might see brecciation of a granite. You might see stockworks in a brittle basalt. And you might see all of these in the same mine. They just reflect different rock types reacting differently to the same fluid. That doesn't make these different deposit types. They are the same deposit type. It's just the mineralization style can vary depending on the host rock. I don't want to spend a lot of time on this, but many of you may look at this and say, oh, those are epithermal deposits. There's a lot of recent papers that are erroneous looking at these deposits here, such as in the Superior province of Canada or the Golden Mile in Western Australia, and saying, oh, these are not orogenic deposits. They're giant epithermal deposits. That's not the case. These are not that common in these deposits. And epithermal style mineralization reflects low pressure mineralization in an epithermal environment. But low pressure can also happen at great depth. We have high pressures, fluid pressure exceeds rock pressure. You break open the rock during fault fill vein formation, and briefly you have very low pressure, and you may deposit silica that looks epithermal, but it basically is low pressure silica. So we have to be careful. Now, the metamorphic model is very well accepted. I don't have time today to talk about isotopes and fluid inclusions, which all show this, but certainly changes in metals as you go up metamorphic grade are important. This is the South Island of New Zealand, the Otago schist, which is filled with orogenic gold. These are the orogenic gold deposits, including the 8 million ounce Macraes deposit. These are the elements that are enriched in these. And as we move from relatively unmetamorphosed rocks up to amphibolite facies, all the elements that are enriched in gold, all the elements that are enriched in the gold deposits decrease in the country rocks. These metals are part of the metamorphism of the country rocks. How does that happen? Well, at the green schist amphibolite boundary, chlorite and biotite release a hell of a lot of fluid, 3 to 4% of the rock. So you have a lot of water. Also, if you look at a greywacke or an argillite, it may have 3 ppb gold or 8 ppb gold, but that gold is not in the quartz, it's not in the feldspar, it's not in the micas. That gold is in your syngenetic, diagenetic opaques, your diagenetic pyrite. When you take a laser and zap that pyrite, it may have 500 ppb gold. It may have a part per million gold, and that's why your rock has 6 ppb gold. So when you metamorphose a rock and release a lot of fluid, a lot of water at the green schist amphibolite boundary, also pyrite breaks down to pyrrhotite, and that releases a lot of sulfur. That sulfur also carries the gold, the arsenic, and other elements out of the pyrite into a metamorphic fluid. So metamorphism of an oceanic rock will always create the right fluid to form orogenic gold in medium grade conditions. And if those fluids are focused along a major structure, you're going to have orogenic gold. Now, people like to say, okay, there's one model. And we know orogenic gold forms in a subduction-related setting, but there's so many ways to form it. You can have crustal thickening and heating as hot rocks are thrust over low rocks. You can have extension as you have slab rollback extension and hot mantle is brought to shallow levels. You can subduct a slab window as plates are spreading apart and almost have a blowtorch to the mantle, heating these accreted oceanic rocks. Especially in the Precambrian, mantle plumes may be important. You have to study your own belt. For example, in Segovia, you have to understand the tectonics of that setting to understand how the deposits formed. They may be metamorphic in origin, but there are so many different ways to heat those rocks. The key is heating oceanic rocks for the first time above 400 or 450 degrees to release the water and the sulfur and the gold into a metamorphic fluid. And depending on the geometry of your origin, the model can vary greatly. And so even if it's an orogenic gold deposit, even if you believe it's metamorphic, the model that you have will be specific to your orogenic belt. Now, most orogenic gold deposits look like this, as I showed you earlier. They can have fault fill veins and extensional veins. They're very laminated often, showing hundreds of events forming these. In places, they can have massive sulfide, though generally it's 2 to 5% sulfide. And most orogenic gold deposits are mesozonal. That means they form at 6 to 12 kilometers depth. And I think, you can look at Segovia, look at the veins there, no different. These don't look like your porphyry type veins that would form at the top of a granite. These look like your basic mesozonal orogenic gold deposits. Now, one thing that is a little different, I did point and mention that they can form shallower than 6 kilometers or deeper than 12 kilometers. That's generally not the case, but it does happen. If they form at 3 to 6 kilometers, they'll be brecciated or stockwork type because the rocks are very brittle at low temperature. At high temperature, rocks are very ductile. So you don't form the big quartz veins because you don't have the big pressure drops to get silica out of solution. So you have more replacement style mineralization in what's called the hyperzonal environment. And so the mineralization looks like this. You may have sulfidation of an iron rock, but not a lot of big quartz veins, but lots of silicification, replacement style mineralization. And because these are higher temperature, sometimes you have calc-silicate mineralization. You'll have biotite, you'll have calc-silicates rather than sericite and carbonate, which are more common in mesozonal orogenic gold. Those are skarn minerals, but these are not skarn deposits. They're not related to a granite releasing fluid in the carbonate at shallow levels. So skarn minerals, but not skarn deposits in a hyperzonal environment. And as I said, the shallow epizonal deposits either form at 3 to 6 kilometers are more brittle, and you have these stockworks and brecciation. One thing that's important in these epizonal deposits, unlike the intrusion-related deposits, where you have telescoping and you can have mercury and antimony and gold all together because you go from high temperature to low temperature, the geothermal gradient controls metamorphic fluids. And so above about 3 kilometers, you may not get hotter than 220 degrees, and you can't carry gold at those type of temperatures, but you can carry mercury and antimony to shallower temperatures. Now, if you have massive mercury near the surface, you may be at 150 degrees. You can't even carry antimony. But if you have massive stibnite, say at 3 kilometers depth, and it's about 200, 220 degrees, that may be the tops to epizonal orogenic gold. And many examples of this. We can look at Donlin Creek in Alaska. When I started working out there, it was called Snow Gulch. It was just a massive stibnite, shallow deposit. We noticed, though, that, it didn't look like an epithermal deposit, and now it's a 40 million ounce orogenic gold deposit called Donlin Creek. And I wasn't the first person to point this out. Lindgren, the famous economic geologist more than 100 years ago, said, I look at the batholith-hosted gold deposits in the California Mother Lode, and they look like this giant New Amandine mercury deposit, which is the largest mercury deposit in North America. They both have silica carbonate alteration. They both have the shallower Mother Lode deposits have the same structural style as the mercury deposits, and they are similar. We can look at the world's great orogenic gold deposits of Central Asia, such as Muruntau in Uzbekistan, Kumtar in Kyrgyzstan. There's all these massive stibnite deposits in between in southwest Kyrgyzstan. They're going to be the tops to shallow orogenic gold deposits. So in the epizonal world, massive stibnite is very important. Now, many people like to say, I'm doing a study, and they think to publish a paper, they say, I'm going to find the precipitation mechanism for the gold deposit. There is never just the precipitation mechanism. Many things are all happening at the same time. The reason we see all these quartz veins, especially in the mesozonal levels, is because of the drop in pressure. With a drop in pressure, silica is relatively insoluble and comes out of solution very easily, and that's why we have these big quartz veins. But look here, just because we have a drop in pressure to deposit the silica, the drop in pressure, look what happens to gold solubility. It does not decrease. It stays about the same or slightly increases. So even though the silica is coming out because of drop in pressure, the gold is not. And the same with temperature. We know temperature is not declining, but even if temperature declined, where gold is traveling with sulfur, gold solubility doesn't decrease with temperature, only where it's traveling with chlorine, which isn't the case here. What's important is when these fluids react with the wall rock, the pressure drops, you deposit silica, the chemistry changes. If we have gold with this solubility here, you can see an increase in pH, a decrease in pH. Fluids may be moving into a more oxidized rock like a granite, a more reduced rock like an argillite. All these decrease gold solubility, as well as the fluids reacting with the wall rocks to sulfidize the wall rocks. So change in sulfur, redox, pH, all happening at the same time, partly driven by the drop in pressure, are what deposits the gold and other metals. So there's never just the precipitation mechanism. Lots of things are happening at the same time. Now, unlike intrusion-related deposits, also, what does paragenesis even mean in orogenic gold deposits? You may deposit silica during this pressure drop, then you may have more fluid coming in. It may dissolve some of the quartz and reprecipitate it and deposit some of the gold. Then you may fracture again, deposit more silica, then more gold, then maybe some base metals, then more silica, then more gold. So paragenesis in an orogenic gold deposit may just be in your little polished section, but in these deposits that form from hundreds of events over millions of years, where you have lots of quartz episodes, lots of gold episodes, you go, what does paragenesis even really mean? Now, another thing that's important is people like to study pyrite in orogenic gold and say it really tells us a lot, but often it does not. And here's the reason. If we look at different types of gold deposits, gold at lower temperature with arsenic goes into solid solution in pyrite, and you have refractory gold. So your epithermal and kaolin type, your low temperature gold deposits here, have a lot more gold in solid solution in the pyrite because arsenic and gold are going into solid solution. That's why all the gold is refractory at kaolin. At higher temperatures, 3 to 4 order magnitude less solubility of gold in solid solution. So you may have a little gold in solid solution in pyrite, but most of your gold is going to be free gold. It can be small nanoparticles you may not see, but it's still free. And most of your arsenic is present as arsenopyrite. And so again, if we look at the amount of arsenic and gold in pyrite, in epithermal and kaolin deposits, it's high, but solid solution in orogenic gold deposits is low. So when people study pyrite grains, which we know form from many events of sulfide and pyrite forming, zoning in pyrite during all these hydrothermal events, and they start trying to make studies of solid solution gold and where the gold came that you see as free gold, that is meaningless because most of this solid solution gold in this pyrite is the waste that goes to the mill. If you have 85% recovery, it's the more free gold or the gold in sulfides, but not the gold in solid solution in sulfides. And so these studies of gold and pyrite in orogenic gold are fairly meaningless. If we look at mineralogy of orogenic gold, again, I said it's generally 2 to 5% sulfide. It's generally pyrite, pyrrhotite, or arsenopyrite present in all of these. Pyrite is present, is dominant especially in Precambrian deposits or granite-hosted deposits. Arsenopyrite tends to be dominant in more sedimentary Phanerozoic deposits. Pyrrhotite tends to be dominant in the higher temperature orogenic gold deposits that form over 350 degrees. Most orogenic gold deposits have some tungsten, tellurium, bismuth. That has nothing to do with magmatism. Tungsten, tellurium, bismuth move in moderate to high temperature fluids, whether they're magmatic or metamorphic. Most orogenic gold deposits have some base metals, copper, lead, zinc. Sometimes they're more associated with areas of gold, but they're always very small amounts. Orogenic gold deposits never yield base metals. They're not produced from orogenic deposits. The byproducts of orogenic gold, besides being just gold, antimony in the epizonal deposits can be very important. Two deposits in Northeast Russia, orogenic gold deposits, produce 10% of the world's antimony. Tungsten is very common in orogenic gold. Tungsten moves in a orogenic gold in a metamorphic fluid because it comes from the breakdown of rutile. So if you have sediments that have rutile, you're going to have tungsten in an orogenic gold deposit fluid. And tungsten has been recovered from orogenic gold. And as tellurium gets more and more important, we're starting to recover tellurium from orogenic gold deposits because tellurides are present in most orogenic gold deposits. People look at orogenic gold, and besides gold being laid in quartz, often they see tellurium being laid in quartz or stibnite being laid in quartz, and they say, oh, it must be a later magmatic fluid because the tellurium and the antimony always seem paragenetically late. But no, it's the same fluid and more pulses. What happens is you may deposit silica, you may deposit gold, you may deposit lots of pyrite and arsenopyrite. Then the next pulse of fluid comes into a vein and reacts with the earlier pyrite and arsenopyrite. To get tellurium out of solution, to get antimony out of solution, you need to drop temperature, which we said does not happen for tens of millions of years during uplift, or reduce the fluid. So if the next pulse of fluid getting into the quartz reacts with the early pyrite and arsenopyrite, it'll help get the tellurium and antimony out that didn't come out earlier. That's why it always looks later than the pyrite and arsenopyrite and much of the gold. But it's not a different fluid. It's the same fluid. It's just reacting with the earlier minerals. Now, the alteration in orogenic gold is very consistent. Most of the mesozonal deposits, it's sulfide, carbonate, and cerussite. The cerussite often is datable for argon dating. As we get to higher temperature, though, into the hyperzonal deposits, rather than carbonate and white mica, we might get massive biotite, or we might get calcsilicate where we have replacement. Again, these are just high temperature alteration minerals. This is most common, but this is possible in the hyperzonal world. If we look at alteration, there's also provinciality to it. I can go where I've been working in North China, and every deposit is surrounded by a broad alteration halo of K feldspar. I can go to central Lapland, and all the orogenic, you cannot find an orogenic gold deposit unless it's surrounded by lots of albite alteration. You can go to many of the deposits in the Abitibi belt in Superior, Canada, in the Superior province of Canada, and all the orogenic gold deposits are surrounded by kilometers of carbonate alteration. Is this a different fluid? My feeling is that it's the original fluid, and the first thing it does is react with the wall rocks, and depending on the chemistry of the fluid in the wall rocks, K feldspar, albite, carbonate, forms over a broad region adjacent to these large faults. That makes the rocks more brittle for the next pulse of fluid to fracture them, form the quartz veins, and then the process continues. So a lot of these orogenic gold provinces have a broad regional early alteration. Now, one thing we're starting to find in orogenic gold is multiple ages. This is just an example from a recent deposit in Finland where they said this small deposit formed at these different times by dating different minerals. Over 100 million years, this deposit formed from different fluids over 100 million years. That just doesn't make geologic sense. Once you lose that metamorphic fluid, you're not going to form this again. And a lot of these ages we're seeing not just here, but everywhere as people start dating magnetite, rutile, xenotime, every mineral they can find. A lot of these ages are at times where things were tectonically or geologically dead. So just because people are coming up with dates, we may not understand some of the isotope gains or losses, and you have to be careful. I think many of the absolute dates you're seeing in the literature make no geologic sense. And rather than assuming the absolute dates are correct, we might try to better understand the geology and also why some of these dates are relatively meaningless when it comes to the age of the deposit. So we have to be very, very careful. We're getting flooded with weird dates now in the literature. One last point about orogenic gold. When I started, this was the field of the 25 largest orogenic gold deposits in the world 30 years ago. Today, these are the 25 largest orogenic gold deposits. We're mining these at much lower grade and much higher tonnage. We're actually mining orogenic gold now at the same grades and tonnages as many of the great gold-bearing porphyry deposits on the planet. A lot of this change reflects issues of sustainability, as we must now help the local people, improve their lifestyles. We have to worry about the environment. We have to worry about politics. And so it's a big investment to start. And you can no longer just mine small deposits, even if they're high tonnage, without a lot of these concerns and a lot of investment. So there has been a change over the years. That's led, though, to confusion in the literature. When I started, most orogenic gold deposits looked like this. Today, many look like this. You may have just disseminated mineralization with gold and pyrite or arsenopyrite. They haven't found the major fault system yet, and people call this intrusion-related. Why? Oh, there's a granite nearby. Or Carlin-like. Why? It's disseminated. But they're in a metamorphic belt near a major structure. And so what should be an orogenic deposit is called all sorts of things in the literature. So we have to be careful now that we're mining these lower grade deposits. I mentioned this earlier, Paracatu in Brazil. We're mining 20 million ounces of hypogene now at 0.4 grams per ton, which is pretty amazing. And then there's always questions, why are some deposits so large? Why is your Frontino belt so important? You got to look for different things in understanding why a deposit is so large. This is Muruntau, the world's largest orogenic gold deposit in Uzbekistan. And you want to look for strange things. There's an east-west fault here that goes for 2,000 kilometers. There's major splays off it, the biggest splays you see on the map of Asia. And that may be important. These terrains are usually clastic that have orogenic gold. A piece of Siberia broke off, floated in as a terrain. And we have carbonate north of Muruntau. You often don't see that in continental margins that are active. Maybe that is like karst, very permeable, and maybe that brings in a lot of fluid. Or the Russians talk about some of these argillites having incredible backgrounds of 100 ppb gold. If that's the case, maybe with that high background, you metamorphose those rocks, you get more gold in the fluid. Maybe all three are important, maybe one's important, but large deposits, you want to look for things that are different. And why are provinces so rich, like West Africa? Here, for example, you could see all the deposits in West Africa are just loaded with organic rich material. And a lot of these Paleoproterozoic terrains, such as the Black Hills of South Dakota, Finland, and here in West Africa, Northern South America, are loaded with this graphitic material. We rifted those Archean continents in the Proterozoic, squeezed them back together. These marine basins had lots of organic matter that concentrates the gold and the arsenic and the antimony and the organic matter and the diagenetic pyrite. And that is probably a good reason why places like West Africa are so gold rich. I want to talk about Cordilleran type belts because they continue throughout the Americas, whether we're talking about Alaska, California, Peru, or Colombia. We have these large subduction-related batholiths. Let's start here in Western North America. These are all the accreted terrains that make up the North American Cordillera. We have these large subduction-related batholiths, and we have our large orogenic gold deposits, the Willow Creek Province, the Juneau Gold Belt, the California Mother Lode, sitting along the margin and within the margins of these subduction-related batholiths. They're favorable hosts. For example, here's the Coast Batholith. This is Juneau I showed you before. Here are the gold deposits. Here's our subduction-related batholith. And the deposits sit along the edge of the batholith for 200 kilometers, similar to what you see in the Frontino Belt in Colombia, and again, related to changes in plate motion. This is the Willow Creek District I talk about here in South Central Alaska. Again, we had a second order shear here off a major sutura. We have a third order shear here, and we have the orogenic gold deposits forming in the margin of this batholith a few million years after the batholith formed and crystallized and was uplifted. So the margins of these continental margin subduction-related batholiths are important to hosting orogenic gold. Sierra Nevada in California, the California foothills, is another example of this, where here we have our subduction-related batholith and the orogenic gold deposit in shears along the margin to the batholith. And finally, I talked about Pataz in Peru a bunch, same story. I think we still have a lot to learn in Colombia about this, but I think we're still looking at the same type of story. We're looking at changes in plate motion in Colombia, about 125 to 70 million years. People like Bob Shore and other people who have worked with him have pointed some of this out. And changes in plate motion is when there's a lot of strike slip along the margin of the Segovia belt and along these faults in the eastern Cordillera of Colombia, and we form the Frontino Gold Belt for 200 kilometers of gold deposits. The ages of these, I admit, are controversial. One of the students from up at U University, Jorge Gambino, now is trying to date a lot of these deposits and is studying these. Actually, he's based in Beijing now looking at these. But it is movement along these faults, especially with the Atto fault, has a trend off the main fault that probably are important in focusing tens of millions of ounces of gold deposits in this Frontino Gold Belt. The ages of these are controversial, but I think some of the best ages by Leo Maja, who's at UBC now, 88 to 80 million, 88 to 81 million is probably the age of many of these. These are in an older, again, Jurassic Segovia batholith, but there still are some ages that seem a little out of sync. Are these real? And that's something Jorge is trying to look at this time. But certainly the orogenic gold deposits are younger than the batholith. Now, workers have argued, because the Gramalotes batholith over here that has some intrusion-related mineralization is about the same age as the Cretaceous Segovia deposits here. Maybe these are related to this intrusion. Besides the fact that I'll show you in the last part here in a few minutes, the depth of these, they can't be magmatic. There's been a lot of strike slip along these fault systems. And some of the arguments, when you look at the tectonics, show that this offset along these fault systems, this batholith at 88 million years may have been 1,000 kilometers away from its present location. So when you try to understand the age of these, you need to look at a map, not of today in 2023. You need to look at a map 88 million years ago. and try to understand the geology when you put these fault systems together. That's very important for these kind of orogenic gold deposits because they're along active continental margins where there's been a lot of shearing along subduction-related batholith. And you have to go back in time, and the spatial associations today do not reflect the geometry at the time the gold deposits formed. So now the last point of this, we can go all around the world, and there is a spatial temporal association of granites with orogenic gold. We can see large batholiths, we can see sills dikes, but when we look at these worldwide, in some belts, the granites are 20 million years older, some belts 20 million years younger, same time, some they're the same age. But that is just meaningless. All it is telling us is magmas and fluids move in orogenic belts as they're forming and being deformed. We may see a sill dike here, and we may have orogenic gold deposits along the margins of these. That does not make a genetic association. It just means melt and fluids have moved along the same structure at the same or different times. A lot of people try to relate orogenic gold to the mantle because they see Lamprophere dikes. You see these in many, many giant orogenic gold deposits, but that has nothing to do with genesis. Again, they predate or postdate the gold, depending on the deposits. And all it's saying is you're near a major structure that may tap mantle magmas. So just because you see Lamprophere dikes in a large pit of orogenic gold, that doesn't mean that there is any genetic association. Yet workers still like to argue for a magmatic model for orogenic gold, even though I showed you that metamorphism at the green schist amphibolite boundary always produces a metamorphic fluid that's going to have gold and sulfur in it. So we have lots of magmatic models where people have an intrusion, and they may form kaolin deposits and porphyry and epithermal deposits and orogenic deposits near these, which make no sense whatsoever. There's a lot of popularity with this tag, a thermal aureole gold deposit, showing some of the great deposits like Muruntau and Telfer being related to distances from large intrusive complexes that crystallized at 8-10 kilometers depth. But again, this makes no sense because at those depths, any fluid is still dissolved in the magma. Do we need magma to form orogenic gold? We know that's not the case. We can go to the South Island again in New Zealand. This is the Macraes mine, lots of gold deposits. But this is an example where metamorphism reached 550 to 600 degrees tops, and there's no intrusions anywhere out here. So we know you do not need to have magmatism to form orogenic gold, because here we have a province without any igneous rocks whatsoever. Yet people, as I said, have talked about Pataz. Pataz gold deposits in Peru are in the batholith, but they formed 25 million years after the batholith. But you can pick up recent papers in good journals like Economic Geology, and they call these intrusion-related deposits and say, well, because the gold's in the batholith, these ages must be wrong. They have to be the same age as the batholith. That actually makes no sense. That is circular reasoning. We can go, again, look at 5-6 papers in economic geology over the last few years of the largest orogenic gold deposit being mined in the Superior province right now, the Canadian Malarctic deposit. It was mined historically underground for 10 million ounces on a second-order shear off a first-order fault. In the last 10 years, they put a large open pit. They started mining low-grade, 2-gram material that was hydrothermal alteration to the original vein system. And in doing that, they found some porphyries that have some veining in these. And all of a sudden, these 20 million ounces were called porphyry gold deposit in one paper, cyanide associated, oxidized intrusion related, stockwork disseminated. It's an orogenic gold deposit, but depending which paper you pick up, it has a different name. So there's lots of confusion. The giant Muruntau deposit in Uzbekistan that I talked about, people talk about it being intrusion related. It formed at a depth of about 8 kilometers. Russians drilled a deep drill hole adjacent to it and hit a granite plug with fresh K feldspar of 4 kilometers depth, or in place to 12 kilometers. Besides not being able to release fluids at that depth, it makes no sense because the granite plug is still fresh, yet people still like to say it's intrusion related. Now, here's the problem with the granite. This is a historic paper by Jake Lowenstern from 20 years ago, and we're going to wrap up here in the next 10 minutes. But let me show you some of this because this is important. If you have a hydrous melt starting to crystallize at 4.5 kilobars or 15, 20 kilometers in uplift, the original fluid that will come out of the melt, giving typical water and CO2 in a magma, would be 42% water, 58% CO2. As the magma continues to crystallize, eventually, as we get to about 1.5 kilobars or 5-6 kilometers, we start to get 90% water, 10% CO2, which is the chemistry of most fluids forming orogenic gold. At shallow levels, you're not going to have a water-dominant fluid, or deep levels, you're not going to have a water-dominant fluid coming out of melt because the water is mostly soluble in melt. Furthermore, the volume of fluid that comes out of melt at these deeper levels is just very small amount of CO2 that probably sits in the melt that goes back into minerals. We don't start losing significant water volume till we're at 1.5 kilobars or a deep moly porphyry depth. And so orogenic gold deposits that are forming at 5-6 kilometers or 12 kilometers, there's no way they can form from a magma because that fluid is not coming out of a magma. So you see paper after paper talking about these orogenic gold deposits, the fluid inclusions, and the structure show they form at 6, 8, 10, 12 kilometers. And then they say, well, there's a granite nearby. It has to be the source. It cannot be the source because the fluid, the water is still sitting dissolved in the magma. And as I showed earlier, any fluid, even if it is released, goes up the mush and doesn't come out the side to form deposits. And our deepest gold-bearing porphyries are about 3 kilometers. So when you see models like this, where you have your CO2-rich, 10% CO2 or whatever fluids escaping the granite at depth to form orogenic gold deposits, it makes no sense whatsoever. Furthermore, people love the fertile lithospheric mantle model now. It's a magic word. You'll see half the papers in our journals now are talking about a mantle fluid forming orogenic gold deposits. 2 problems with that. Where I worked in North America in the young terrains of California all the way to Alaska, there's no enriched continental lithosphere. Below all these terrains, the geophysics shows oceanic crust and oceanic sediment on top of the oceanic crust, and no enriched mantle at depth. So from North America, we know you don't need fertilized lithospheric mantle. That may be important to form porphyry and epithermal deposits where you have a metal and fluid-rich granite that is the source of these intrusion-related deposits that form in the upper 3 kilometers. But you don't need fertilized mantle lithosphere to form orogenic gold. Furthermore, if that's the case, how do you get that fluid out of the mantle lithosphere to form orogenic gold? People argue, well, the mantle melt moves up and releases the fluid. But as we showed, those mantle melts can't release fluid till at least 4 or 5 kilometers depth. So they can't do it. And then other workers argue, well, a metamorphic fluid escapes the mantle and goes up the faults to form these. but a fluid coming out of the mantle will be carbonic. Most of the water will go to form melt, and any mantle fluid will be almost all CO2 and not water dominant like the fluids that form orogenic gold that are 90% water. So it makes no sense whatsoever, yet we see people arm waving and putting that in the literature. Just to wrap up on a few other deposit types that are confusion, Carlin type deposits. Because there's a model just for Nevada, we don't understand these well, but this is what country rock looks like. This is a high-grade Carlin deposit. That's another reason they're hard to understand. You can look at what some of the important workers on Carlin deposits have said. Some said magmatic, some said meteoric, some said metamorphic, but they don't look like high sulfidation or low sulfidation epithermal deposits. They don't look like orogenic gold deposits. And every Carlin deposit is associated with lots of organic matter, lots of petroleum migration. And I think if you ask me, my bias is heating of this organic matter is the way we form these different type of deposits. Yet the most arguments out there still call for a magmatic origin because there are granites at 10 kilometers depth, and they talk about fluids at 10 kilometers depth coming out of these magmas and forming these shallow Carlin deposits 1 to 2 kilometers. Again, the same problem. How do you get fluids out of a melt at those depths? You can't. And so that model for Carlins makes no sense. We also have something called reduced intrusion related gold systems. Most gold deposits are of magmatic origin or oxidized intrusion related systems. Your porphyries, your skarns, your epithermal deposits. Those are all associated with copper rich oxidized magmas. In the year 2000 though, a deposit called Fort Knox near Fairbanks started to develop. It was a more reduced S-type granite like you would see associated with tin deposits. It has sheeted veins that are 0.6 grams per ton. There was a road system near Fairbanks. There was a population that was very pro-mining, and there was a good power grid. So all of a sudden, this was economic. It wasn't a new discovery. It was known for 100 years. And that led to the reduced intrusion-related gold system model. But most tin, tungsten, reduced intrusions have little burps of gold associated with them. It's just not economic. But once Fort Knox went into production, and there's a few deposits nearby in Yukon, these granites with these low-grade sheeted veins where you could mine for 0.5 gram per ton led to a new model called reduced intrusion-related gold systems. I don't think they're anything you would explore for. They're only being mined, as far as I know, in the Yukon and adjacent eastern Alaska, and they're just not good targets. And you may have sheeted veins with many tin granites, but again, they're just not being mined. If you bulk mine these, you get, 0.6 grams per ton, and if you have everything else okay, they're mineable. A lot of papers in the literature talk about reduced intrusion-related deposits, but then you read about these, such as Vasilkovskoye in Kazakhstan, which is huge. It's an oxidized granodiorite. Many of these are just sheared margins of reduced intrusions or oxidized intrusions. So you have to be careful. The Fort Knox reduced intrusion-related model has been used for many gold deposits, but then you read about the deposit, and basically they're sheared orogenic gold deposits on the margins of oxidized intrusions. So just to wrap up, if we look at orogenic gold deposit in geologic time, about half the gold endowment is Precambrian. It is late Archean. It can be about 2.8 to 2.5 billion, or 2.1 to 1.8 billion. That's when 75% of our continents that we see today were made, probably associated with super plume events. Those plume events put a lot of greenstones up. that were then metamorphosed and deformed over the next 20, 50 million years and have our orogenic gold. But then beginning at about 1.7 billion years, we have what's called a boring billion. We have no orogenic gold deposits, or very few orogenic gold deposits of that age. The older orogenic gold deposits of Paleoproterozoic and Laocoon remain in the middle of continents because we have thick lithospheric keel that prevents uplift and preserves the green schist facies belts that make up 75% of our continents. But look what happens beginning about 1.7 billion years ago. Instead of forming broad cratons anymore, we start to have Cordilleran-style orogenic belts, such as you have in Colombia, such as we have in Western North America. This is the Grenville Belt, the oldest of these. These are Cordilleran-style ribbon terrains. Around these cratons, as the Earth cooled, we were starting to subduct these oceanic rocks. When we do that, we start to form these metasedimentary terrains around the cratons. But these old metasedimentary terrains have been uplifted. These rocks are about 1.7 to 0.7 billion years old, and they expose rocks that were at 20 or 30 kilometers depth. So not only have they lost their epithermal and porphyry endowment, they've also lost their orogenic gold deposit. That's why the older Cordilleran style belt or accreted metasediments don't have orogenic gold. Now there are always exceptions, and there are a few areas in this time frame that do have green schist facies rocks that haven't been eroded to great depth. Most of these are actually in South America, such as along the margin of the Amazon Craton, where they're being mined along the Brazilian-Bolivia border. Many of these in Bolivia are being mined small scale. So there are exceptions to these. And when I say you're not going to explore in 1.7 to 0.7 billion year old rocks, that holds for most of the globe, but there are a few areas of green schist where there are exceptions. And finally, when we look at the growth of our continents, 75% was produced in these two superplume events. And that's when half of our orogenic gold deposits formed as we form these greenstones and metamorphose them. The last 25% of the Earth's crust are Cordilleran belts, formed over the last 1.7 billion years. The gold in the older part of the belts, the boring billion, have been lost to erosion. The younger orogenic belts that are 700 million years and younger, mostly exposed green schist facies, still have their orogenic gold. And this all fits with the growth of the different supercontinents. And Rodinia supercontinent then basically lacks orogenic gold because most of those Cordilleran belts, again, are high-grade rocks where we've lost the orogenic gold from this new Cordilleran crust. So to summarize, if we are exploring for orogenic gold, you want to look where new crust has been added to continents. It can be forearcs or backarcs. It's often along the edges of subduction-related batholiths. And these rocks have been metamorphosed and deformed within 20 to 50 million years of their formation to form orogenic gold. We want to certainly concentrate our exploration in rocks of Laocoon, Paleoproterozoic, and late Neoproterozoic to present age. We want to think about structure, metamorphism, and the type of traps. We're looking at gold that is in crustal rocks. Marine crustal rocks have been metamorphosed. Many models are possible to heat those rocks. And today, perception and sustainability certainly are some of the more important factors, not just exploration and gold grade. Are there intrusion-related orogenic gold deposits? People love a point source, but if your orogenic gold deposit formed below 3 to 5 kilometers, which almost all of them have, then I don't see how they can be magmatic in origin. I would put them in this bag over here. And finally, what is science fiction? And you need to be careful when you read about gold deposits. Is there a direct association of orogenic gold with magmatism? People love that, but makes no sense to me. Tungsten, bismuth, tellurium, just because you have scheelite, or just because you have scheelite or bismuthinite or tellurides, that has nothing to do with a magmatic source. Radiogenic isotopes tell us where the gold was sourced. They're a total waste because most of those isotopes, like lead, are coming in from the trap. They're not moving in the low salinity fluid. So when you see people do lead isotope studies of orogenic gold, makes no sense. Is there a mantle connection? I don't see how. It makes no sense to me how you get the gold and fluids out of the mantle to form orogenic gold. When we start seeing many different events separated by many tens to hundreds of millions of years for orogenic gold, that makes no sense to me. We have to question the meaningfulness of many absolute dates. When we see late phases like many base metals, telluride, stibnite, and orogenic gold, that doesn't mean it's a separate low temperature episode, but it just means it's a later episode than some of the original pyrite and arsenopyrite. And in some of these Archean deposits, when we see some epithermal-like styles, those aren't epithermal deposits. They're just low pressure textures. So anyhow, I'll leave it at that, and I'm happy to answer any questions.
Thank you so much, Richard. It was a very interesting talk. So I don't know if you guys have some questions. You can put it in the chat, or you can just turn on the microphone and talk.
And I'm also always on email if people want to email me questions.
Sebastián tiene la mano levantada. Si quieres, puedes prender tu audio y haces la respectiva pregunta.
Hola, ¿me escuchan?
Sí, señor.
Hello, Richard. Thanks for your presentation.
Sure.
It was so beautiful. I have a question for you. You talk about the orogenic gold deposits lacks for base metals.
Yes.
But for example, here in Colombia, we have some examples in Segovia and Tolima department. We have like orogenic gold deposits, but those deposits has a lot of base metals and a lot of silver with low gold grades, you know. So in this case, how you can explain the amount of base metals and low gold grades within this model?
Well, I think some of the gold is probably present as electrum. So there is your silver. Many deposits have very low gold fineness, and that may just reflect a lot of chemical issues with the fluid. But the base metals, often many prospectors saw a lot of galena and sphalerite associated with orogenic gold, or in some metabasalts where there's a high copper background, you may see a lot of chalcopyrite. So you can have pockets where you have enrichments of these base metals, but they're never at the tonnages where they would be recovered. Are they being recovered there in Colombia from the orogenic gold deposits, the lead and zinc?
Yeah, yes. Actually, there are some processing plants that actually are recovering the concentrates of the base metals because the sphalerite and galena amounts are too high. So it's economic viable to recover those metals. For example, in Segovia, I know that the plant actually is recovering silver, zinc, and lead.
Okay, well, that is interesting because that may be the only examples I know in the world where that is the case. You know, we have things called Coeur d'Alene type veins, where Coeur d'Alene in the USA is a good example, and there's a few other examples around the world. We're in these metamorphic argillite basins, and instead of having gold dominant mineralization, we have silver, lead, zinc mineralization. And it's still controversial as to why. The fluids are not much more salty, but maybe the argument is that the basement is more enriched in some black, shaly argillite that may have a higher background in lead and zinc and silver, and some of that is being carried in these fluids, even though they don't have high salinity. And the best I can give you, a best idea I can give you is there may just be something local in the basement to give you those lead and zinc enrichments. I would assume the lead and zinc isn't throughout the Segovia belt, it's just in a few of the deposits, or is it throughout the whole belt?
For what I have seen is in the entire belt.
Okay, well, that's unusual, and maybe it is something in the basement where these fluids are coming from that are carrying a little more lead and zinc. Certainly the belt has moved a tremendous amount of gold. You've concentrated at least 30-40 million ounces of gold when you include the alluvial gold. So it certainly is a gold-rich province. It's interesting that you're recovering lead and zinc, but I think that is just, yeah, something we don't understand. I certainly don't understand it, but to me, it is still a gold province, given the large tonnage of gold that you have compared to, certainly it is not a huge lead zinc province where it competes worldwide with other lead zinc provinces.
Okay, thank you, Richard. So finally, for saying, there is a possibility that there is an overprint of epithermal deposits in these cases, like for example, Segovia, because we have seen that the exhumation rates are too high. And maybe the silver and the other metals can be explained by epithermal events, like in other ages, the evolution of the deposits.
I think if there is an epithermal event, you should see a mineralization style that looks like, low sulfidation epithermal veins, and there shouldn't be a one-to-one association with the orogenic gold deposits. I would expect these to be nearer the magmatic centers that have been placed into that Jurassic batholith. If you had some tertiary plugs, I would expect, if you had epithermal mineralization, some sort of spatial association with the epithermal mineralization. But I think both things you pointed out, the epithermal mineralization and the lead zinc, are great sort of thesis topics, great PhD studies for students there in Colombia to work on, because both are unusual and both are very valuable studies that would be important to do.
Okay, thanks. Thanks a lot, Richard.
Sure.
¿Alguien más desea hacerle una pregunta a Richard? O
I think there is a question in the chat. I don't know if, well, the
I have a
question
question.
is,
Okay, sorry.
okay, let's start with the chat and then you can continue, Andres. In the Antioquia batholith, some deposits were classified as IRGT. Also, the exhumation ages are approximately 5 kilometers, are younger than the mineralization, so that are not IRGT.
Yeah, I was at Gramalotes like 15 years ago in the batholith, and I didn't know what to make of it. Yeah, I certainly do not know what to tell you that mineralization is. The only thing that I can tell you with certainty is the batholith at 88 million years was nowhere near Segovia because of the movement along the faults. But many of you may have and a lot of work's been done there since I visited it. A lot of you may have a better idea of what style of mineralization is. I don't even know what an intrusion-related gold deposit is, because people are just really using that term to say, oh, it is a magmatic hydrothermal deposit. And I say, okay, it's an oxidized intrusion. So you're telling me it is a porphyry? Is it an epithermal deposit? If it is neither of those, what type of deposit it is? You were just telling me where you think the fluid came from, but I don't know what deposit type it is. But certainly in that Antioquia batholith, that certainly is an interesting mineralization that, again, is worth good study because I have no idea what it is.
Well, thank you. I think Andres had a question. Andrés López, ¿tenías una pregunta?
Yes, I want to ask you, what are the main differences to separate intrusion-related gold deposit from orogenic gold deposit? What are the more useful techniques, like stable isotope studies, or just microthermometry, or just with uh, mm, visual inspection of the mineralogy, or what can you tell me?
I think geologic observations are probably the most important. Intrusion-related gold deposit, especially with an oxidized intrusion, to me is a porphyry or epithermal deposit. An orogenic gold deposit is something totally different looking. I would just look at those. I would look at the alteration, the mineralization style. Does it look like a porphyry to you? Does it look like a high or low sulfidation epithermal deposit to you? Or does it look like one of these laminated quartz veins that are characteristic of mesozonal orogenic gold? And I think that is much more important than fluid inclusions or isotopes that can be very equivocal in their interpretation. And people interpret in so many different ways. Orogenic gold deposits have many secondary inclusions. People study secondary inclusions that give low temperature and are just have no CO2 and say, oh, then it's epithermal. But no, you're just studying secondary inclusions and couldn't tell the difference. So I think just geologic observations would be very important to me in telling the difference.
Okay, thank you.
Thank you, Richard. Here is another question. Victor asks, the Ote fault, a structure that runs through Segovia batholith, could contain a deposit of orogenic gold?
Oh, absolutely. And I think I may be wrong, you may know more than I, but I think I recall some of the deposits are along the O2 fault. Yeah, certainly I don't see any reason it does not. And if there are gold occurrences along it, yes, it is a very favorable structure. But maybe when I am there next year, we can look at maps, look at some of the structure, and figure out what structures may be most important.
Okay, I have a question.
Yeah.
First of all, Richard, thank you very much for the explanation, for the conference. I just have a little questions regarding the array of the parallel orogenic vein systems we can see in Colombia, especially what we mentioned in Segovia. What would be the explanation to have such a number of parallel array of veins? Like, we're not talking about 2 or 3 major, let's say, trends of veins, but we're seeing 20, 25, 30 veins separated by, let's say, tens of meters. Like, what would be the explanation? Because maybe we see different characteristics in those veins, and those are being mentioned to be related to different ages of mineralization. So would this be like different episodes of, let's say, faulting and precipitation along those structures, or how does it work? So in this kind of systems?
Yes, they would be different episodes. You know, you may plug up one part of a structure and then you'll fracture another. Many of these deposits, they mine hundreds of big veins in the same area. And you continually pumping fluid along those structures, but also as you deposit silica in some of the veins, you're causing the fluids to go in different directions, different permeabilities, because you are sealing the fracture. So you're often going to have a series of veins, not just one main vein. So what you're describing is very typical of many deposits, such as in the Juneau Gold Belt. I showed you that one intrusion with hundreds of different veins in there, and those were all very large. The California Mother Lode shows the same thing. In the Pataz batholith, in one deposit at Pataz, we'll have lots and lots of brecciarin veins. So what you're describing is very common. Remember, you're pumping fluid over millions of years into one spot, and you're continually breaking the rock, and you're continually making the rock hard with carbonate or albite or silica. And so you're going to have all sorts of veins form, because once you make it hard and re-break the rock, you have huge pressure drops from maybe 4 kilobars to a few bars for a very short time. And that just drops out lots of vein material. All that silica comes out of solution.
Okay, just a comment over there. So it doesn't matter that, let's say, the veins are really thin, like centimeters wide, because that's one of the reasons why people think Gramalote, it's an intrusion-related deposit, because you're finding hundreds of veins just inches wide, and the same happens in the northern area of Segovia, because people think that when they are looking for orogenic gold deposits, they are looking for meter-wide structures, like, mega structure or central veins within the system. So it doesn't matter that they're just arrays of really thin structures. It doesn't matter that, is it that way?
Absolutely not. And sometimes thin veins are better because there's more reactivity with the wall rocks when you have so many little thin veins. So you sulfidize the fluids more easily, that can be really good. Murantau in Uzbekistan is lots and lots of small little veins. So that I don't think that has anything to do with whether it's intrusion related or orogenic. I think it just has to do with the plumbing system and how those fluids reacted with the rock.
Okay, Richard, thank you very much for the comments.
Sure.
Well, anyone else has a question?
¿Alguien más quisiera hacer una pregunta a Richard? Por el chat, micrófono.
I think we have 5 minutes more, maybe, if anyone has a question. If not, maybe we can just end the meeting over here.
Si no es así, entonces se dará por ya finalizada la conferencia. Entonces, le queremos dar las gracias al señor Richard por impartirnos la conferencia tan importante para nosotros.